Thank you so much for inviting me to participate. So I'm going to talk about effects of dietary composition on nutritional requirements, but this is not going to be a talk with a whole bunch of answers that I've figured out. It's a whole bunch of questions that I've started asking about what we think we know about what we need. And when I say dietary composition, I mostly mean what effects are going to change when you go from a grain-based diet to a low-carb diet. And I'm also going to touch a little bit on plant-free diets, since that's a pet hobby of mine. So the kinds of things that can change our nutritional requirements include just adding certain compounds or nutrients even that cause interference. And I think of the interference in two different ways. So there's bathtub interference, where you have some component in a diet that's acting actually like a drain on another nutrient, causing you to need more to compensate. So an example of that might be phytates. The more phytates that you're adding to your diet, the more minerals, particularly zinc, that you might need to compensate for that. But it's not a two-way thing, like taking more zinc doesn't make you need more phytates. So for that kind of paradigm, I think of it more like a scale. So you take more sodium and your potassium requirements would go up, or you take more vitamin D and your vitamin A requirements might go up. So that kind of dynamic. And then in terms of compounds and nutrients, there can be, instead of a subtractive effect, there can be an additive or synergistic effect. So this could be looked at from two, kind of an optimist or a pessimist point of view. So one contribution of one nutrient can lessen the requirement for another, but it's also the case that a deficit in one can increase the requirement of another. So choline and folate, for example, can spare each other in the methylation function in particular. But sometimes it's just in one direction, and it's more like being, you can't really ride this bicycle without the front person, but maybe you can ride it without the back person. So, for example, the RDA for magnesium is trying to cover the case where your protein needs are not completely met. But as far as I know, just getting enough magnesium doesn't actually spare protein, but it's possible. And then besides just those actual component interactions, there's this whole can of worms of all the different metabolic pathways that are going on. And if you're going from a diet where you're primarily getting your energy from glucose, a whole different set of pathways are going to be primarily active than if you're getting most of your energy from fat. And that could change what's produced in terms of enzymes and cofactors and hormones and fatty acids and glucose itself. And all of those can have different demands on your nutrients. So I'm going to go through a whole bunch of examples where a low-carb diet might result in a change in your nutritional requirements compared to a high-carb diet. One that's fairly well known and even recognized by the HWO and the FAO is this thing that I mentioned before about a high phytate diet, which is going to really drain your ability to take in zinc. And so in their document on fortification and all of the different nutrient deficiencies globally that you might want to address, or that they do want to address, one of the nutrients they talked about was zinc, and they described a low zinc bioavailability diet as one that's high in unrefined, unfermented, and ungerminated cereal grains, especially when animal protein is negligible. And a diet that's got a lot of soy protein would also be a candidate diet for a zinc deficiency. But how do we quantify the effect that that's having? I don't really know, but if you look at the Institute of Medicine document where they try to figure out what the RDA should be for all the different nutrients, one thing that they do point out in the section was that in vegetarians, the factors in a vegetarian diet can be so detrimental to zinc absorption that the requirements for dietary zinc could be as much as 50% higher. And if you think about that, that's comparing a grain-based diet that's omnivorous to a grain-based vegetarian diet, and even there you get a 50%, possibly a 50% detriment. And think about if you take away all of the grains and legumes from the diet, how much less zinc you might need. It could be really quite substantial. So it needs to be tested, of course. The next one I want to just touch on is iodine. This diagram comes from a paper in which it's being argued that because when we started on an agricultural diet, our carbohydrate level went up very, very high, that this might have impacted our iodine requirements very severely, because on a low carbohydrate diet you use a lot less T3. And it's not that it causes hypothyroid, it's just that because of glucose not being predominantly used, you just need a lot less T3. And he estimated that the T3 requirements could actually go down about 40 to 50% based on a variety of studies in low-carb situations. Now, of course, all of the iodine that you get isn't used in the thyroid, but it's most of it. So to make the thyroid, the T3 hormone, it's maybe about 70 to 80% of the iodine in your diet goes to the thyroid to make T3. And so if you put those numbers together, if you go on a low carbohydrate diet, your iodine requirement could be as much as 30 to 40% lower than it would have been on a high carb diet. All right. So the next one is really interesting. This chart, I've taken data from this study, and I've doctored it into this graph to make the units match. So normally you wouldn't talk about tens of micrograms per deciliter of free fatty acids, but just so you can see for each case the magnitude of the change. These are results from when you go on a ketogenic diet, the free fatty acids before you go on the ketogenic diet, and the free fatty acids that are available after, and then how much is reflected in the actual phospholipids. So this is consistently found that all of the free fatty acids, not just DHA, go up tremendously on a low-carb diet. And many people think, well, okay, it's just because it's being released from the adipose tissue. And there are some animal studies that suggest that might be the case. But there's another idea that I had about it. So to make DHA, we have this conversion that can happen in mammals, and the limiting step in it is this delta-6 desaturase. And so if you don't have, if you only have a certain amount of delta-6 desaturase, there's only a certain amount of DHA that you can possibly make. So it turns out that delta-6 desaturase is actually upregulated by PPAR alpha. And PPAR alpha, of course, is intimately involved in ketogenesis. So if you're on a ketogenic diet, then your delta-6 desaturase may well go up, and this may increase the rate of your own ability to take linoleic acid for arachidonic acid, which also goes way up, and linolenic acid, and turn it into DHA. So that's a very speculative idea, but I'm wondering if that might account for some of the changes we're seeing as opposed to just drawing more of it out of the adipose tissue. Another thing that seems to change in the blood is folate. This puzzled me for a long time. The first time I ever heard anything about it wasn't really about a ketogenic diet. It was this study where they had folks in Ramadan who were simply not eating in the day, so it's just intermittent fasting. And they did this nice little control where they have the people who didn't fast during Ramadan at the top and the people who did fast. And then they took blood levels of various things before and during and after. And one of the significant changes that they found was the level of folate in their blood went up more than 25%. And vitamin B12 as well. And they didn't control their diets. They did take dietary logs, and they didn't notice anything in particular that would be increasing the folate levels. You can't completely discount that idea, but it looks like the folate just went up, and where would that possibly be coming from? And I saw another study. The table was very hard to read, so I just reproduced it here. And they measured various things. These are the micronutrients they looked at. The only significant ones that they found different were again folate, again another 25% increase. Iron went down a little bit. They didn't give any information about the diets. The only thing they said was intake of 12 of the 21 evaluated vitamins and minerals changed significantly, and I don't know if that means that the intake was the factor here. But then last year, this study came out. This was actually their picture that they put on it. They were studying fatty liver disease, and they happened to have noticed before they did their study that folate deficiency is highly associated with fatty liver disease. And so they specifically looked at the actions on folate in these ketogenic dieters. And they, in their study, they determined that the increase in folate levels, which they also saw, was actually coming from gut bacteria synthesizing it. And didn't have access to all of their tables, but if you look here, we have again, the serum folate that goes up from just over 20 to just over 30. And on this side, we have all of the different pathways that they noticed being activated. And so the circle, the size of the circle is supposed to represent how much it changed. And if it's this yellow and brown color, that means it increased. If it's the blue color, that means it decreased. Here is the folate biosynthesis line. And then they highlighted a bunch of different bacterial synthesis pathways that they think were involved in increasing the folate. So it seems like even if you're fasting, your folate, you actually get more folate by not eating than by eating, which is really, really interesting. All right. Now I'm going to talk about vitamin C a little. This excerpt is from a fascinating issue of The Lancet from the 1800s. I really would love to read to you all of the different back and forth that went on and the issues that were involved, because it's so interesting to see all the different speculations and ideas. But I will indulge in reading you this one. Sir, I was struck by two independent observations which occurred in your columns last week with regard to the etiology of scurvy, both tending to controvert the generally received opinion that the exclusive cause of that disease is the prolonged and complete withdrawal of succulent vegetables from the dietary of those affected. Thus, Mr. Neal of the ERA Arctic Expedition says, I do not think that spirit or lime juice is of much use as an antiscorbutic, for if you live on the flesh of the country, even I believe without vegetables, you'll run very little risk of scurvy. Dr. Lucas writes, in the case of the semi-savage hills tribes of Afghanistan and Baluchistan, their food contains a large amount of meat and is altogether devoid of vegetables. The singular immunity from scurvy of these races has struck me as a remarkable physiological circumstance, which should make us pause before accepting the vegetable doctrine in relation to scurvy. These observations do not stand alone. Arctic voyagers have long pointed out the antiscorbutic properties of fresh meat, and Baron Larey, with regard to hot climates, arrived at the same conclusion in the Egyptian expedition under Bonaparte at the end of the last century. So there was all this contention if does meat by itself cure scurvy. A lot of people were saying that it did. I think that's still believed to be true. And this came up in my little niche recently because I belong to this community of people who aren't eating any plants. And people new to the scene say, well, aren't you just going to get scurvy? Well, scurvy appears within 1 to 3 months. And I know people who've been eating basically like liver-free, some of the, I don't know whether they're crazy, I love liver, but diets of mainly just muscle meat, and they're not getting scurvy, and how could that possibly be? And so that's why I had started looking into this. And everyone knows there's no vitamin C in meat, right? But the USDA has charts for every every line that you read in their database. You can go and find the document of how they measured it. So this is, for example, beef rib. It's very long because it has all the nutrients. I cut it off here so you can see this vitamin C line, and it doesn't matter. You include the fat, you don't. You cook it, you don't. There's no vitamin C in it. Source code 7. This source code shows how they measured it. Assume 0. They didn't measure it. They just said, oh, there's no vitamin C in beef. If you look at salmon, they'll show a little vitamin C. But if you look at beef or pork, they don't show any, even though there is vitamin C in the flesh. Now, it's not a lot. I was able to find this old study in a German book that was looking at vitamin C in different tissues and of many different animals, and the skeletal muscle one is here. So if you think that maybe beef is somewhere between the ox and the sheep, it's maybe about 2 milligrams per 100 grams. And you need about 10 to prevent scurvy, some say 6. So that's going to be something like 3 to 500 grams, maybe a pound to get your vitamin C needs met. And people in the carnivore community do eat that much meat, typically because they're not eating anything else, right? So they're going to eat a pound of meat a day. But it just seems really borderline, right? And then if you take into account the fact that when you dry it or age it or cook it, some of the vitamin C is lost, it still seems like there's a bit of mystery left. John Speth, I think this is just about to be released, made this recent paper trying to figure out the same mystery for the Neanderthal and for early hominids who were eating a meat-heavy diet at least some part of the year, and saying, how can they not be getting scurvy? And he thinks that they did this by eating raw, by eating all the organs, and one of the things that the paper is mostly suggesting is that we must have putrefied meat. The reduction in the pH allows the vitamin C to not be destroyed in the same way that it would if you just aged it. So I guess in the northern climes, they do preserve meat this way and like it quite well. When we want to find out things about vitamin C, we literally use guinea pigs as our guinea pigs because they are one of the few other animals that don't produce vitamin C endogenously. Most other animals do. Primates don't. Guinea pigs don't. There are a few bats that don't. So this study that I'm quoting here, most of the time, or in the studies that he had done previously, when you give a guinea pig a diet completely devoid of vitamin C, they will die in 3 weeks. And he took a group of guinea pigs, gave them a diet completely devoid of vitamin C, but also gave them glutathione esters. After 40 days, they still had no signs of scurvy. It's not even that they weren't dead; they just were normal. And he chalked that up to the fact that glutathione can recycle vitamin C and spare it to some degree as well. So if glutathione is recycling the vitamin C, then I wouldn't say necessarily indefinitely, but at least for almost twice as long as they typically would live, they were still living and not showing any signs. And one thing that we know about ketogenic diets, well, no might be too strong a word, but there is some evidence that a ketogenic diet does increase glutathione levels. And so you could make a case that when you're on a very low-carb diet, that your vitamin C stores just simply last longer because they're being spared by glutathione or recycled by that. Another thing that could come into play on a low-carb diet with vitamin C is this fact that the receptor, the transport for vitamin C, this DHA is not the fatty acid DHA, it's the transport form of ascorbic acid, dehydroascorbic acid. They compete for uptake in the cell. This was shown back in 1975 by Mann and Newton, where they actually were doing infusions of glucose and showing how the absorption of the vitamin C was going down and down the more but the glucose was coming into play. And so another group of researchers made this proposal about heart disease and diabetes and comparing it to scurvy. They were saying, this is just like what you see in guinea pigs with latent scurvy. When they're about to develop scurvy, there are all these things in common. So you have these signs of atherosclerosis, you have increased histamines, you have increased cholesterol, you have decreased carnitine deficiency. And so they are making the case that diabetes and heart disease are a form of tissue scurvy, and that's why diabetics will develop wounds that don't heal, and that kind of connection. They also said this just struck me. I'm not really going anywhere with this, but one of the mechanisms that they talked about when they were comparing atherosclerosis with scurvy is they mentioned that vitamin C stimulates the barrier function in the endothelial cells, and I didn't know that. And they put it down to collagen synthesis. So what about collagen? Some people said, well, okay, all these people who are eating a lot of meat and not much else, they're getting collagen directly from the meat, and maybe that's why it's sparing. But I don't think this can happen because digestion breaks down the collagen. And even if it breaks it down only into hydroxyproline, studies both in vitro and in vivo have shown that if you get hydroxyproline into the bloodstream or just into the cells, it doesn't get incorporated into the collagen. Just as an aside, I wanted to say that this new product, collagen hydrolysate, may actually be a different case because they've specifically done this patented thing where they break it down into particles that are longer strands that have been shown by tracer studies to actually make it into tissues. The reason, just briefly, why I think that that hydroxyproline itself isn't going to make it into the tissues is because of the order in which it's made. So you have these polypeptide strands are made mostly out of proline in the very first step, and then it's hydroxylated. So if you give hydroxylated proline, it doesn't even get considered for this first step, so it just doesn't make it into that pathway. That's what I think it's going on. But what about carnitine? There are many things that vitamin C helps to synthesize, but the main things are collagen and carnitine. Carnitine is very important for fatty acid transport, and if you have a carnitine deficiency, you're going to get very, very tired. And it turns out that the first symptom of scurvy before you start bleeding and stuff is just extreme fatigue. And so maybe the carnitine intake from all the meat is actually sparing one of the processes for vitamin C. That turns out to be actually a lot more plausible because when you eat meat, up to 75% of the carnitine is absorbed. It's less if you have enough carnitine, but if you don't have enough carnitine, you'll actually take in a lot just by eating meat. So carnitine intake could be one of the things that's sparing the need for vitamin C in these cases. All right, so who cares? Does any of this matter? You might run into a weirdo like this and say, look, here's what I do, and it solves a medical problem for me. So back a few years ago when I started eating a plant-free diet, most people weren't even hearing of that, and it didn't matter. But it's become really popular in this tiny niche. I'm not sure how to talk about popular versus unpopular, but if you think that when you say autoimmune protocol, people are going to roll your eyes. Well, imagine that. Imagine how I feel. But I do it for a reason, because I've just found empirically that it drastically improves this major condition that I had. And a lot of people that are doing this diet are doing it for autoimmune reasons. And people who were on the autoimmune protocol took out the plants, and suddenly all all of their problems went into remission. A lot of people are finding that. So if you're going to be talking about that and doing that, all of a sudden people are going to say, well, how can you sustain yourself on that for the long term? Yeah, sure, maybe you want to do it for the short term, but isn't it going to be detrimental for nutrients? And maybe it is. It's hard to say. But some of these issues about nutritional requirements changing may come into play. You can't just necessarily look at RDAs. One of the reasons is that RDAs don't take nutrient interactions into account. One of the reasons is that RDAs were developed on a skewed population, a high carb population, a grain-based population, and arguably a sick population. They also are incorporating preventive measures for diseases that happen in people eating high carb diets. So if they say, well, we want to decrease your risk for cardiovascular disease or for diabetes, then they say, well, if you look at vitamin C, for example, the RDA for vitamin C is not the antiscorbutic dose of 10 milligrams, it's 60 milligrams. And if you look at the document in which they developed that recommendation, all those other grams are based on this speculative idea that adding more exogenous antioxidants is going to help with metabolic syndrome. Whereas if you think about the hypothesis that it's hyperglycemia is causing a vitamin C deficiency, it makes sense that adding some vitamin C might be able to help that. But on the other hand, if you just take away the hyperglycemia, maybe you don't need that. So there's different reasoning. And then sometimes, since they're supposed to be looking at all the different nutrients that we know about, sometimes they can't even find a way to determine what the RDA should be because there's no way to compute the balance. You take people off it and nobody gets sick. And so what they've done is said, well, this is what people eat and this is about how much they get. And so we're going to say the RDA is that. And that's the case for example, manganese. But a much bigger problem with RDAs in particular is that they're designed to show inadequacy, or to show adequacy rather, and not inadequacy. And that sounds the same, but let me put it this way. If you were going to take a trip across the desert for 2 days, you knew you're going to need some water, you calculate it out, you think, I think maybe I need about 5 liters of water. You're going to take 10, right? You're not going to take 5 because you want to cover the worst case scenario. But just because you take 10 doesn't mean that you actually believe that if you have less than 10, you're going to not have enough. It's just that you're being extra cautious. The RDAs were actually developed not to try to prove how much each person needs, but for situations where, like, they want to provide food for the military, or they want to provide food for a group of refugees or a starvation time, and they say, we want to completely cover a basis so that there's no child left behind, right? There are very few people, if you give them this diet, that would ever come up with a deficiency of anything. So there's a huge buffer built into the whole measurement. So actually what they're trying to hit is about 2 standard deviations. And that means that for the average person, the RDA for a nutrient, they need almost like half as much in some cases as what the RDA says. So you can't look at a diet and say, oh, you're only getting to about half the RDA, you're going to be inadequate. What you can say is maybe some people are not going to be getting enough, but the average person probably is. The RDAs are abused when they're being used to evaluate a diet to say that for an individual, they're probably not getting what they need. To cover a population, maybe that's the right thing to do. But if you think about people like us who are being very conscientious about what they eat, if you think about the fact that you've taken out all the phytates out of your diet, you're very healthy, what are the chances that you're over here? They're probably pretty low. Once you've dialed into a really healthy diet, you're probably closer to here. And so the use of RDAs is a little bit, we have to be careful about what we're talking about when we use them. So I just want to talk about some theoretical implications besides the practicality of evaluating diets in the real world. So this is a slide from Cordain and some others who were trying to determine how in our Paleolithic past we could possibly have been getting all the nutrients that we needed. And there are a lot of different nutrients. He was only mainly really trying to constrain how will we get enough energy for our brains and how will we get enough long-chain fatty acids for our brains, DHA in particular. So he had this list of different foods that might be available at the time. And so if you want to get your energy needs met, just eating wild plant foods or even tubers, which are really locked up in fiber, you're really not going to get enough energy. Nuts, you can get a lot of energy out of, and ruminant fat, you can get a lot of energy out of. The problem with nuts is they don't have DHA to speak of. So you could make an argument that you could get some of your DHA from fish and get your energy from nuts. That's a good balance. I think there are recent hunter-gatherer societies that use exactly that strategy. But he then argues the freshwater fish probably, the evidence doesn't show up that we had access to that until much later. And so he says ruminant is actually complete nutrition because you can use the subcutaneous fat for energy, you can use the muscle for protein, you can use the liver for a variety of other nutrients, and then you add the brain in, you've got the DHA, you've got everything that you need. So he makes this argument here. He made it in another, or they made it in another paper later, which I used this one because it has that nice table. And in the later paper, Stephen Cunnane writes to the editor and says, I don't think that this is enough because our brains are the evidence. And if we didn't have enough DHA, but it's not just DHA, there's also iron and iodine and selenium and all kinds of other things that we would have needed to evolve our brains. And so if we don't now have the evidence that we had access to fish, we have to let our brains be the evidence because we couldn't possibly have evolved them otherwise. So we must have had more access to food than we now.
Why was it eating another brain?
Pardon?
You could eat another brain, right?
Well, that's what Cunnane was arguing.
Okay.
And I think, or sorry, that's what Cordain was arguing.
Okay.
I think Cunnane is saying it's just not enough and it's not enough iodine. And so there's this kind of friendly short back and forth about whether the shore-based idea was necessary for us to have been able to evolve the brain. And I only bring it up because I'm thinking if we didn't have a high carbohydrate diet at the time that we're talking about, maybe these needs that Cunnane was basing this idea on weren't as high as we believed that they were. Maybe if the iodine was dropped to 60% of what we believed it was, if we had more ability to convert our own DHA, then maybe this hypothesis is less needed. But I don't know, I would, in order to develop that argument, I would really have to find out all the quantities involved, and I certainly, I don't think I'm going to knock down Stephen Cunnane's whole body of work, which I think is amazing. But it just called that into question in my mind about maybe the whole debate is a little spurious if we had more access to the nutrients in the very foods that were there, just because what we were eating caused our requirements to shift. So that's all I've got, a whole bunch of questions and no answers.